Okay. Hello, everyone, and thank you for your great support of the NYU Wireless Industrial Affiliates. It's my pleasure to be here to tell you about some of our research we're doing at NYU Wireless on what I call the spectrum frontiers, terahertz. Actually, it's, as you'll see, 100 gigahertz to 800 or 900 gigahertz. But we're deeply grateful for your support. And we wouldn't be doing this work if it weren't for the great industrial affiliates. And you'll be finding out soon from our director, Tom Marzetta, that we have a lot of exciting things happening this year, including our board meeting in April and also some other big events happening later in the year. So you'll want to make sure you get the board meeting on your calendar with the date. I think that's either been sent out or will be sent out shortly. So today I'm going to talk briefly about terahertz. What do we mean by terahertz? Well, if you look at the millimeter wave and terahertz range, millimeter wave goes 30 gigahertz to 300 gigahertz, and terahertz is that band 3 gigahertz. It's 300 gigahertz all the way up to 3 terahertz. That's what's formally known as terahertz. But in wireless parlance, we typically talk about terahertz as above 100 gigahertz, or sub-terahertz is the 100 to 300 gigahertz range. Interesting thing is that terahertz is up at around 1 gigahertz is about 2 orders or 2.5 orders magnitude below visible light. Optical light is 430 terahertz to 790 terahertz, which is just below the ionizing frequency bands of ultraviolet, X-ray, and gamma ray. So terahertz is still 2 to 3 orders of magnitude below where we know there's ionizing radiation and moving up above millimeter wave. It's interesting on this graphic, which is a few years old, there's no applications for wireless up at millimeter wave or terahertz. But the fact is millimeter wave now is 5G. So this cell phone needs to move to the right to be under millimeter wave. And wireless is going to go to terahertz, as I'll show you shortly. Well, we got a big boost in the US when the FCC opened up its spectrum horizons in 2019. And NYU Wireless was a big part of that conversation in the years preceding that big announcement. And the FCC opened up these commercial Wi-Fi bands. These are now available today to any one of your companies to make products, unlicensed products. There's EIRP specifications, there's allocation, it fits in the World Radio Conference allocation. So these are open for business today and have been for a couple of years now. And what's really cool about that is we're opening up spectrum here in the 100 to 200 gigahertz range. And what I wanted you to see is that this 100 to 200 gigahertz band that the FCC has just opened up is really the beginning of what I think will be 6G and 7G. We have clear sailing, I believe, all the way up to several hundred, 800, 900 gigahertz. And look at this graph to see why I say that. You know, the whole world of sub 6 gigahertz is down here at the far left, where the attenuation due to air on our Earthlink mobile link is fractions of a decibel per kilometer. And here's the 60 gigahertz, which we always thought was high attenuation. But look at 100 gigahertz and 200 gigahertz at sea level in dry air and even up at high in the atmosphere. If you're at sea level and it's dry, there's no moisture, look at the attenuation. All the way out to 800, 900 gigahertz, it's still less than a dB per kilometer. Now, the fact is we have moisture in the air. Unless you're in the Mojave Desert, you're going to have some moisture. So it's worth looking at the blue curve. Notice how the atmospheric pressure, the temperature, that's where sea level comes in, and the moisture content, W, impacts attenuation. So here we are at sub 6 gigahertz, even up at with moisture, there's no attenuation to speak of. But going up to 100, 200, 300, even out to 800 gigahertz, if you look at the troughs of these curves at sea level and high up in the troposphere, if you look at the bottom edge of these curves, you see that the attenuation at most, if you pick a bottom, is only like 10 dB per kilometer up to 300 and 400 gigahertz. 10 dB per kilometer is only 1 dB per 100 meters. 1 dB is barely noticeable on a microcell. So we get a microcells up to 300, 400 gigahertz, and even up to 800 and 900 gigahertz. Look at this, we're at 100 dB per kilometer, and that's 10 dB per 100 meters. So even up to 600 to 900 gigahertz, we're looking at frequency bands that, due to air, we're only going to have basically 10 dB per 100 meters over today 4G cellular. Now 10 dBs over 100 meter, I'm going to show you, is very easy to make up with antenna gain. So not only that, but the rain factor, which we worry about for 5G, flattens out above 100 gigahertz. So once you design wireless systems for 50 or 70 gigahertz, you've designed them for rain all the way up to 1,000 gigahertz, up to a terahertz. That is, rain doesn't have any more impact because the size of a raindrop is now very large compared to a wavelength once you get above 70 or 80 gigahertz. So that's amazing. Basically, mobile will go up to hundreds and hundreds of gigahertz. And all the engineering that all of you done, all of you NYU wireless industrial affiliates have done to make 5G happen, will just take us all the way up, now another order of magnitude of frequencies from 30 and 70 gigahertz up to 300 and 700 gigahertz. And what's fascinating is if you look on the right, the rain attenuation is an impact, but it's the atmosphere going up to satellites that really causes attenuation. That is, once you start going up the atmosphere to space, you lose the impact. You lose this wonderful lack of attenuation. You get much greater attenuation as you go higher and higher in the atmosphere, as you add rain. But see, this is only out to distance greater than 10 kilometers. So on Earth, if we're on Earth, free space path loss and the loss due to this atmosphere is really not terribly different. This is at 140 gigahertz at one of those low curves. But even at 300 to 500 gigahertz, we're going to be able to do very long distance point to point as well as mobile. So the big takeaway from the previous graph, this one, and the graph I'm going to show you next, is that when we're up here at 100, there's really not a lot of loss, even in terrestrial fixed links. You're a bit less than 10 dB per kilometer all the way out to 400 gigahertz, which is amazing. And even out to 900 gigahertz, we're not going to be that impacted if we can use antenna gain. So the real big thing is rain. Rain is going to be limiting you. And as I said, once you design for 5G, you're designing rain out to 6G and 7G up to hundreds of gigahertz. Now, I want to make sure everyone on the call realizes this, that the way the world thinks today is you think that you go higher in frequency, you get more path loss. That's how the world thinks. More path loss as you go higher in frequency. You guys have to dispel this myth right now, because that's only when you use an omnidirectional antenna. In fact, when you use directional antennas and keep the aperture the same, when you keep the same physical size of the antenna and you go up in frequency, what you see is that the blue curve 140 is stronger. You get stronger received signal at higher frequencies than lower frequencies if you keep the aperture of the transmitter and receiver antenna constant. The whole world and all the textbooks, except our millimeter wave book, hasn't figured this out. But you all should know this by now, that it's the directional channels that allow these high millimeter wave and terahertz systems to work better. That is, to have greater path loss per hertz, better path loss performance, more signal to noise ratio as you go higher in frequency, not less. So this idea that you get more lossy at higher frequency is totally wrong by physics. Now, it's true that walls and glass and brick, they're going to attenuate much more at the higher hundreds of gigahertz than they do at sub-6. That's true. But if you're in free space, or if you're bouncing off things and you're in air, you actually do better going to higher frequencies. Now, what's interesting about this regime above 100 gigahertz is we have a lot of passive satellites that are operating above the troposphere. And there's this natural attenuation that occurs in the sky going above the troposphere. You get this great attenuation such that these satellites, which are very, very sensitive receivers, they need to be protected. These satellites basically will not see energy from Earth if the path is on a long slant path. That is, if you look at the beam angle, and this is at low angle on the horizon, but this is straight up overhead. At the low on the horizon, Earth transmissions on Earth, there's hundreds of dB, even thousands of dB. Let me say that again, thousands of decibels, unheard of. So there's this natural attenuation between these very sensitive satellites that are looking at Earth and moisture and water droplets and studying the Earth from above that are operating above 100 gigahertz, and the potential for future mobile links that operate on ground. In fact, if you could just keep the energy on the ground, Earth won't interfere with these passive satellites. Now, the Millimeter Wave Coalition is an industry organization. NYU was the first academic member. It's growing rapidly. If your company's not a member, consider joining the Millimeter Wave Coalition. This is a graph they just put together. It shows all the available spectrum globally already authorized by the ITU. And the blue bands are where the FCC got out in front of the whole world and created the first unlicensed bands above 100 gigahertz. Europe, with Ofcom in England, has just followed suit and matched these 4 spectrum bands. So these are open for business, and a global standard is starting to form at these 4 bands that the FCC opened up. Now, I don't have time to go through it all, but the slides will be available, and we've just had papers published on this. But during COVID, we were able to conduct some of the world's first measurements at 142 gigahertz over large distances on the NYU campus, and even created surrogate satellite measurements that show this idea of not interfering with space and how much multipath might bounce off the buildings in a campus or urban environment. So these are some of the measurements. I'll go through them real quickly because I'm almost out of time. But we deployed transmitter sites at the exact same locations that George McCartney used back 3 years ago when he did his 73 gigahertz comp measurements on our campus. We've now recreated those measurements at 140 gigahertz, achieving great distances, remarkable coverage, very similar to 73. And here were the students conducting the work. We got on the roof. We were down around the courtyard. You can see on the right an antenna, which is a surrogate satellite. And it's also not just a surrogate satellite, it's also a surrogate backhaul. So we were interested in seeing how much mobility would interfere with a backhaul network that was operating kind of above the earth, linking tower to tower. Will mobile transmissions in the same band interfere with that backhaul? And you can see various setups that we conducted here during the last year. Here's an upshot of some of the results. Very exciting to see that 140 gigahertz, the path loss over microcell distances is virtually identical to what we measured at 73 and 28, except for the first meter propagation distance. That is, all the loss is coming in that first meter. This is without the antenna gains, so you can put back antenna gains and make up for that, for whatever loss you need to. But the bottom line is the path loss exponent, the large scale fading in terms of signal degradation is virtually the same as at 5G 28 gigahertz as it is at 140. And we're studying the various reflectivity and scattering properties of materials. And here were the first satellite surrogate measurements, where on the building on the left, we had a high base station receiver. And then we put transmitters around campus, and we, at those transmitters, measurements 1 through 10, we pretended those were mobile transmitters, and we looked at the elevation angles. If we kept the mobiles elevated on the horizon versus elevating the mobile antenna patterns. And what we found is very rarely, if the transmit mobile had an elevation angle that was up, it could actually bounce off a building and cause a multipath component. But by and large, this graphic shows that if you look at the blue curve at the bottom, if you could keep the mobile antenna patterns on the horizon at 0 degrees over many distances and many locations, you can see that it's 40 dB below what their theoretical free space path loss would be. That is, you get 40 dB of isolation, roughly, from keeping the 30 to 40 dB isolation by keeping transmissions on the ground on the horizon and not beaming up. Of course, when you beam up on the mobile transmitter, you start getting antenna pattern leakage into that receiver up on the roof. That's a surrogate satellite. Now, that's not even counting the hundreds of dB additional loss that the troposphere gives us to a satellite. So the upshot is, in this early experiment, it looks like you're not going to get multipath energy going up to the sky or to the backhaul. Finally, we're looking at biological health effects because no one really is doing it. NYU is able to do it. We've done a lot of work below 30 gigahertz, and ICNIP, the non-ionizing radiation committee, just came out with guidelines, and no one's really tested to see what terahertz radiation would be regarding these guidelines, that if we build practical antennas. So we're starting to look at practical antennas, practical systems, trying to figure out if we know that heating is the major concern, and to test heating, we can use the same methods we used for 5G, where we model the skin and muscle. But we also can do measurements. And so we're gearing up with the medical school to be able to study these. And we've already been studying them on smartwatches to see what the heating is using MRI. Let me conclude by showing that we're also starting to consider animals to see if there's behavioral changes when exposed to sub-terahertz and terahertz radiation. And we're starting to look at how we would do those experiments. So in conclusion, 5G's happened. You guys helped make it happen. We're needing to lead above 100 gigahertz. We're doing that. If you've followed the slides, I hope you believe with me that there's clear sailing up to 800 gigahertz with all the work going into 5G. Interference mitigation, protection of autonomy, doing link designs for backhaul is key, and then health effects are something we're looking at. With that, I'll conclude and answer any questions. I hope it came out okay. Did everyone hear me?
Yes, you came through loud and clear. If you have any questions, feel free to unmute yourself and speak.
Good afternoon. Yes, the idea of keeping the aperture the same as you go to higher frequencies means you have a narrower beam. Is there a pointing challenge you get there then? Or
yeah, no, that's a good area of research. Pointing will be an issue. And so you can imagine acquisition being with wider beams, less gain, maybe more power, and then resolving the pointing once you've kind of locked on. So yeah, that's a very fruitful area of research.
Have you looked at squint at all at these very high frequencies with very narrow beams? Is that going to be an issue?
Yeah, it probably will be somewhat of an issue. We published a paper using some really reduced arithmetic logic with a colleague of mine, Arjuna, because we're considering in the future when you have so many more elements, you're going to need that computation will be significant. So ways to reduce that computation will be useful. And you do have some squint issues, but I think they're all achievable. I mean, they all can be baked in. You know what I mean? We'll deal with them like we've always dealt with squint.
What about the other question I had is there's still export controls in the US above 94 gigahertz. Is that going to change?
Yeah, no, we were able to get an exemption due to our research. We ran it through NYU legal and got a ruling. So everything we're doing, as long as we make it published and open, and that's why it's so vital. That's why it's so critical that you as NYU wireless industrial affiliates help bring other industrial affiliate sponsors to our center, because there are research exemptions if you make everything available publicly through a research consortium, which is what we are. So we need you to be able to continue to do this. But that's something we're very cognizant of. Both bandwidth and carrier frequencies are export control. Let me ask you this, are there anyone on the call, were you skeptical 10 years ago? Were you skeptical 10 years ago when I said we'd have millimeter wave wireless? Anyone willing to admit they were skeptical? So,
yes.
Who was that brave soul who said yes?
It's John Cowles here, but I think a lot of us were. So
Okay.
I probably don't speak just for myself.
No, I love that, John. Thanks for your candor. Well, they started shipping the iPhone 12 with millimeter wave transceivers in it. You know that. So hopefully you'll maybe be less skeptical that we're going up to 800 gigahertz. I mean, all the technology needed to put 28 gigahertz in this iPhone and 60 gigahertz in Wi-Fi will give us the dividend to do that up to higher frequencies. So I expect there are people working on Wi-Fi access points right now in these new FCC bands, bringing the integrated circuit capability, the RF amplifier efficiency, the antenna issues, the pointing issues, all that is going to come. And we're continuing to work on that, and we appreciate your support. Other questions or thoughts?
I'd be concerned that we would have electronics that would work up at 800 gigahertz.
Yeah, well, there's a DARPA music program which is working on RF amplifiers up to 500 and 600 gigahertz, dealing with all those packaging issues, dealing with the heat dissipation because the elements become so small. You can imagine an active integrated antenna with the RF electronics and the elements physically being smaller than the transistors used to produce RF. So there's all these packaging, heat dissipation issues to create those electronics. So many fundamental problems, but that's why we're in business. That's why you're part of NYU Wireless. We're working on those things. My colleague Sunday Brangan's working on, on this SRC project JUMP. I mean, there are a lot of people working on this area, and we're focusing on understanding what's possible, what the channel can do, so you can do the link budget, so you can figure out what the antennas will be. Pointing will be a good issue. We'll have PhD students working on, but we will build this. We will build it. It is viable. I mean, the fact is, we went from concept to putting it in an Apple 12 in a decade. That was kind of the icebreaker. Once we went up one order of magnitude, we'll go up another order of magnitude. It's kind of like we just discovered Moore's law. Moore's law, when integrated circuits started to scale, we're starting to scale in frequency now in wireless.
Do you see a need for lensing in addition to phased array kind of steering?
Yeah, I'm sure lensing will be used probably at base stations. I think lensing makes a lot of sense. It's very energy efficient, packaging efficient. Yeah, what do others think? But yeah, I agree. As we go up higher, that's going to make a lot more sense.
Or even metamaterial kind of work.
Absolutely. Metamaterials, changing frequency bands over hundreds of gigahertz is going to require new thinking. There'll be new technologies to be able to do that. I mean, look at the Wi-Fi bands that were just opened up above 100 gigahertz, going from 100 to 250 gigahertz. It's a huge span. So you're going to need smart materials. It's a ripe area of research, frankly.
You talked about the applications that you can envision.
Yeah, I didn't.
Can you elaborate on those? And then the other question is looking at network architecture and how that changes to take advantage of these different applications. Do you see big shifts going from 5G to 6G and above?
Yeah, it's a good question, Mark. Thanks. And thanks for your good support at Crown Castle. The fact is, 5G is going to probably be a lot like 3G. It shows that the web might be possible, but then 4G is where the web really became on every cell phone. So 5G, I think, is going to be more about faster data rates and making a superb 4G and just showing the hint of what 6G will be. And then 6G will usher in all these amazing applications. I won't spend a lot of time on those, but I wrote a whole paper on it. If you Google my name and look up 6G challenges and opportunities, if you Google 6G challenges and opportunities, NYU, or my name, there's a number of pages given to some of the exciting applications. Some of them are see in the dark imaging on your phone. We'll be able to use our phone for a night camera. We'll be able to see behind walls with our camera. We'll be able to use the phone to be a smoke detector. We'll be able to use the phone to determine if there's allergens in our food. It'll be an amazing position location device, so we'll be able to replace rulers, or tape measures. So those kinds of applications will come. with 6G, along with all the VR and AR and all the massive bandwidth. I think also the Internet of Things, connected Internet of Things will really take root at the end of the 5G era and more towards 2030, when you'll see this rapid expansion where everything in your car, everything in your house is connected. There'll be so much great data rate, and there'll be so much position location capability. There'll be so many features that will all become part of the phone and your Wi-Fi and your cellular network. And you know, as the electronics advance and the power efficiencies occur, you'll see that come in.
So one of the challenges still for 5G is actually getting it to have enough energy around corners, for example, on streets. And this is much lower frequency, much wider beam widths, and a lot of reflections. High frequency, go to narrower beams, you're going to have a lot more difficulty with that. So that issue with 5G, millimeter wave 5G, hasn't really been resolved adequately until this point.
Right, it's going to be though. It's going to be the beam steering algorithm in the first 5G new radio is inefficient. They're making that much better in the next release or next version of 5G. So the antenna pointing is going to be a lot better at finding and locking on to the multipath. Right now it's pretty clunky, but that will be fixed over the next year or two in the standard. So the idea of exploiting the directionality in the handset and the base station will become more prominent and will solve some of those problems, because you're right. Right now, if you don't lock on to a path that exists when you're obstructed from your current path, if you don't get there fast enough, it looks like it's pretty shoddy, and then it has to take, you know, a quarter of a second to find where the new one is. But that's going to be fixed.
Yeah, I'm just wondering, with narrower beams, you're going to have less, of those scattered signals to look for.
Well, there's a lot of reflection. There's a lot of reflection in the millimeter wave channel. And as you go higher in frequency, you get less. So your point is a good one as we go higher and higher in frequency. But for the 5G millimeter wave, there's a lot of multipath that has good strength. So the key is to just find that multipath. And the multipath exists. I mean, you're right, we get shadowed when we go around corners, but in an urban environment, if you go around a corner, there's generally another building or a lamppost nearby that's going to provide a scatter or a reflection, a strong signal, when you lost one that you were originally listening to. So yes, it's a challenge, but adaptive antenna technology and channel state information, knowing where the multipath is and finding it and tracking it, is how you overcome that. That's really the key to that. And the beam being very directional, I mean, you can imagine dithering narrowing the beam down in real time very, very rapidly, very rapid, to improve your signal to noise ratio. Those kinds of things will become part of future wireless standards that don't exist today. But you don't need a very wide beam width at all. You want as narrow as possible to lock into the energy when you find the signal. So finding the signal will be the tough part. And then locking on, things move relatively slowly compared to data rate. You know, the channel moves very slowly once you've locked on to where the energy is coming from.
How about reflections? Have you looked at reflections and what kind of level?
Yeah, we've published a number of papers on those. If you just Google NYU wireless scattering and reflection, you'll find some papers. We did study up to several hundred gigahertz, and we've measured at 28 and 73. And we're building a ray tracer that will be making available to all the industrial affiliates as we develop it. It's in early stages, but it's looking very promising. So yeah, we've published on that. We've studied the reflection pretty well, and you can find that in the literature. And by the way, all industrial affiliates should have access to our affiliates only publication database where you can search on terms and access all our papers for free. That's part of your membership.
So,
Really good questions. Any other thoughts or comments or questions? Nothing else? Okay, well, thank you all very much for your great support of NYU Wireless. Tom, you're on the call. Do we know the board meeting dates in April, or are we finalizing those with the administration?
That's being finalized, but we'll be sending that information out shortly, Ted. It will be the latter part of April, however.
Okay, great. Yeah, we'll look forward to seeing you. I don't know if we'll be on campus by then, but certainly it'll be virtual and you don't want to miss the board meeting. And do please socialize NYU Wireless and the work we're doing amongst your colleagues and competitors, you know, where you want to see pre-competitive research funded. It's hard to do work like this. It's very expensive. So, you know, we put every dollar of your industrial affiliates towards the students that do the work. And it's hard to do work at these frequencies. So we really appreciate your support. And you can email me directly if you're having trouble finding the papers or you want any specifics. Feel free to email me at TSR. My initials TSR@nyu.edu. I'm at your service. All of the faculty are at your service.